So this talk is called Modern Problems Require Modern Solutions, Finding Your Meme Twin with Embeddings in Vector Databases. My name is Guy Royse. I'm a developer advocate at Redis. Spoiler alert, we're going to use Redis in this talk, but the bulk of this talk is going to be about image embeddings and how you can create them, how you shouldn't create them, what they are, how they work, and just get an intuitive understanding for as a developer of what embeddings are, and specifically with image embeddings. So this talk is going into some data science territory. And so I always like to preface this. Well, I'm going to start with a joke. I have a data science joke. And it's what is a pirate's favorite programming language? You might think it'd be ARM80, but his first love be the sea. It works better when everyone participates. Come on, people. Now, the thing that I actually like to do when I start any kind of data science-oriented talk is to say that I am not a data scientist. I am a developer. I've been a developer for a long time, but through variances in my education, I did not spend a lot of time studying a lot of math. And so I'm not particularly mathy. I don't have a data scientist background, and it's just not what I do. I'm a developer who uses data science tools, which is probably most of you in this room. And so I'm not a data scientist. Some of my details could be wrong, but they'll be true enough for you to do your job. Is anyone in here a data scientist? Well, what I meant to say is that I'm totally a data scientist, and you should listen to everything that I'm going to say. So I am something of a data scientist myself. So I've got 4 main things I want to cover in this talk, and really kind of a theme. I got 4 agenda items. Is 4 agenda items a lot of agenda items? Well, it depends. For a talk at a conference? Not at all. For a talk with your boss? Yes. I want to talk about 4 things. Well, I'm going to talk about what an embedding is, so you can just understand what these things are. Anyone can use a model and generate an embedding and put it in a vector database and query it. That's not terribly complex coding, but understanding what it actually is you don't have to understand what it is to use it, but it'd be nice to know what they are so that when it doesn't work right, you can know why it failed. I'm going to talk about how to use them in your code, how you can make them yourself, and why you shouldn't. And then we'll have a code and demo at the end. Everyone, if time permitting, will have a chance to find out who their meme twin is. So the theme that I'm kind of going for here is that this is a data science talk. So that means Python, right? Wrong. I've done all of this in JavaScript. There's 3 things that I'm trying to dissuade people from when it comes to working with a lot of these new tools. One is, you don't have to do it in Python. You can be sad like me and do it in JavaScript instead. There are tools in lots of languages to do this. This is not the exclusive domain of Python. 2, you can run them locally on your machine. You do not have to put these things in. This is just not a bunch of cloud APIs. So all the models that I'm running are running locally on my Intel-based MacBook. I don't even have Apple Silicon. I got an Intel one. So this is like 4.5-year-old MacBook, and it runs just fine. And then the third thing is you don't need to plop down a credit card to spend 5 cents a day using OpenAI APIs. You can run them locally. And so this is very, very accessible to developers. So those are kind of 3 themes that permeate a lot of these talks that I give. So let's get into first, what is an embedding? Hopefully, at the end of this talk, I will not be the only one around here who knows what embedding is. By the way, I took the meme images and put them in Photoshop and had AI extend them out to fill them up to be 16:9 aspect ratio. And I think it's really funny that it put another gun barrel there on the right. That's not every bowling alley that I've gone to. So, what is an embedding? Well, before I want to get into embeddings, I want to talk about data. I want to talk about the 2 types of data that we work with as developers. There's structured data. This is the data we've been working with our entire careers. It's things like numbers and strings and locations and things that are very easy and discrete and that you can just say, is it equal to, or is it greater than or less than, or is it within a range of, that sort of thing. This is every column you've probably ever put in a relational database, structured data. And then there's unstructured data. unstructured data, up until recently, has been kind of hard to work with. I mean, you could store it and you can put it on a screen, but you can't extract anything out of it. There'd be things like documents, text, prose. I mean, you can search with like keyword search in prose, but if you want to, say, find all the documents that reference the fast food restaurant, someone has to have labeled that as fast food restaurant, or you need to look for every keyword in there and see if fast food is in there, but then it wouldn't necessarily find McDonald's, even though we all know that's a fast food restaurant. This unstructured data is historically been hard for computers and easy for humans. Images. Does this picture have a cat in it or not? Is it a hot dog or not a hot dog? Did I just violate the code of conduct? I'm sorry. Those sorts of things. Those are historically hard for computers, easy for humans. And things like audio. Like, is this song good or bad? Maybe that's a bad example, but this sort of unstructured data is hard to pull information out of. It's hard to query. We know how to deal with structured data. We've been using it our entire career. What you do with structured data is you store all of your company's structured data in SQLite. Is that what everyone around here does? Yeah? Well, maybe you store all your company's structured data in Access. Or perhaps you put it in Excel. That's where I used to work. Turning unstructured data, however, into something meaningful requires a little bit of processing, requires some embedding. And so here I have two examples of unstructured data. I have a meme caption and I have the meme picture. Don't need to debug your code if it doesn't compile. This is me as a JavaScript developer. And so if you want to take text and turn it into just data that you can operate against, you can go through several processes. You might run it through an LLM to summarize it. So maybe it's really long. Maybe you've got an entire book and you really just want to have like 500 words. You summarize it, shorten it down so the model can deal with it. You'll tokenize it, pull those words pull all those words apart and all the letters and symbols in there. So like, take the word, the quick brown fox jumped over the lazy dog. Lazy might be turned into two tokens, laze and y. Or period at the end of the sentence is a token. So we're pulling these tokens out so that we can feed them into a model. And then we run them into an AI model to embed them. And what that model does is it spits out a pile of numbers. A pile of numbers is the embedding. It's a vector. It's literally just, depending on the model, it's just literally an array of floating point numbers. Same thing for images. You take an image, you transform it, you put it to a particular resolution, maybe put some black borders on it so that it's square and the model can deal with it. You run it through a series of convolutions to identify features in that image. Those convolutions then create output those features, which become the embedding, and it is an array of numbers again. And so this is a way of turning documents and pulling the meaning that's in them, or pictures and pulling the meanings in them, or sound and pulling the meaning that's in it, into an array of numbers. And if these numbers are similar, then the thing that you have an embedding of is similar. So if I have a picture of someone pointing their head, and I get a certain set of numbers, and a picture of someone else pointing their head, but maybe on the other side, I'll get similar but not identical numbers. And then you can compare them. You can think of these numbers as sort of scores. The model has pulled features out of the text or the image or the sound, things that are meaningful to the model. We're going to pretend that we only have two features. Our array has two numbers, and the things that the model cares about is how elderly the person in the picture is and how alcoholic they are. And then you get a score. You get a number from, say, -1 to +1. Varies from model to model, but we'll just use -1 to +1 for this. And so here we have Leonardo DiCaprio with a coupe glass saying cheers. That's probably pretty alcoholic. He's literally drinking a fancy cocktail. I even knew what it was called, a coupe glass. But he's not particularly old, so the elderliness score is down around 0. He's not young, he's not old, he's just kind of middle of the road. Other images could get other scores. Here we have grandma discovering the internet, perhaps one of my favorite memes. Grandma is clearly not alcoholic, at least according to this picture. It's possible she's been drinking too much in the kitchen, and the blueberry pie she's making is going to be a little interesting. But so it's got a very low score for that, but she's clearly quite elderly. So the model extracts these features out of the image. In reality, you've got more features, hundreds of them, depending on the model. In reality, these aren't going to be nice, tidy things like alcoholic and elderly, but this is illustrative. And so you get these sort of these scores of the various things that are in the image, how strongly that trait is represented. And you can treat them like coordinates. So you can take these two here, we've got how alcoholic and how elderly they are, and you can place them on a graph. Now we have two dimensions, we have two values, so we can do this as a two-dimensional graph. If you had a model that has, say, 512 dimensions, or 512 values, you can't draw it, which is why I use two. But those 512 dimensions, conceptually, it's the same idea. And so here we have the very alcoholic, not even toddler there. What I think is funny about the image is that kid looks so British. It just makes it extra funny. And then over here on the right, we got the Dos Equis man, the most interesting man in the world. He's got a bottle of Dos Equis in front of him. He's kind of alcoholic, but not as alcoholic as the coupe glass or the baby. And he's a little bit older, so he's to the right. Bottom left, you just got kids. Bottom right, you just have old people. Top right, you got alcoholics. You know, you get the idea, right? You can plot these out, and all of a sudden, you can see their relationship because you can see them in space. So what you can do with this, and I kind of talked about this already, but this is another way to show it, so I'm going to talk about it again. What you can do is you can take all these images, that all the points, and all the vectors, all the embeddings for these images, and generate them. So the baby success kid has one set of numbers, and most interesting man in the world has another set of numbers, and mocking SpongeBob has yet another set of numbers. And if you want to find things among these sets of images, you can take an image of, say, an old man with a pointer, and create an embedding of that, and then say which set of numbers are more similar. And in this case, it's this one, because I just changed them with my text editor. And so this makes me the most interesting. Usually the thing shows me, as it turns out, is I'm the dad from American Choppers. That's usually how I turn up in the example, but today I came up with the most interesting man in the world. It's about 50-50, but 60-30. 60-40. Math is hard. I told you I wasn't mathy at the beginning of the talk. So how would you compare a set of coordinates? I mean, you could just look at them and say the numbers are similar, but how do you actually do similarity? Well, if you look at this as the chart again, there's a couple different ways. The easiest way is you literally just draw lines. This has got a fancy word called Euclidean distance, but it's literally just the distance from a point to another point. And so if you want to find, take a vector and say which is the most similar, you can find whichever one is the closest. It's literally drawing lines. Pythagorean's theorem in action. So that's one way to do it. Another option is you can use cosine similarity. We've probably heard this term, it's been thrown around a lot. All this is you take the cosine of the angle between the 2 points. The smaller the angle, the higher the number, the more similar the images. These both have some strengths and weaknesses. So cosine similarity can catch generalities. So if they're on the line together, but one's further, they could be really far apart, but they could be in the same direction because one's stronger than the other. But that might be what you want, might not be what you want. Whereas Euclidean distance might find things that are close to each other, but they're not quite as similar as you'd like because they're only close to each other on a couple axes, maybe not others. And so neither one is optimal. There's another option you can do. I don't have a representation of it on screen, but you can do the inner product of the coordinates. And that sort of takes the magnitude of the vector, the point from origin heading out, and the angle into account. It kind of balances out the difference. It doesn't make a nice, neat, tidy graph, though, so it's not on here. Another thing you can do is you can do a range query. So you can say, I've got a point, show me everything within 0.1 or 0.2 of this point, so I can find things that are similar, that are nearby. This is kind of Euclidean, but in the case of if you're doing a search for Euclidean, you would say, give me the 5 closest things. Give me my k nearest neighbors. Whereas a range query says, just give me everything within a radius, which if you're trying to do, say, like a semantic caching, would be very useful because you could get a cache miss or a cache hit. And I'll talk about that more in just a bit. To query these in a vector database, you need to create indices. And there's 2 types of indices that most of the tools I've looked at support, including, uncoincidentally, Redis. You can do a flat index, and this is a perfectly accurate brute force search. And so it simply goes through and creates an index on everything in every vector. In the case of Redis, if you've got about 1 million or so entries in your vector database, this is perfectly performant. Obviously, it depends on your hardware and several things like that. The other option is a hierarchical navigable small world, HNSW. This creates a hierarchical graph that you can follow, and at the top layer, you have a few nodes that you can find using, it's like, we'll find the nearest node. Okay, there it is. And then you go down to another layer and say, okay, now that I'm close to this, find other nodes that are near that, and other nodes that are near that, in a big layers of graph relationships. This gives you approximate accuracy, and you've got arguments where you can make it more accurate or faster or take less space. It's all tunable. And so once you get past about 1 million, you want to start considering these. And I'm not going to go into the nitty-gritty details of what these are. There's documentation for that, and you wouldn't remember it anyhow. Some use cases then for using vectors, embeddings. They're kind of an interchangeable word. I'd say all embeddings are vectors, but not all vectors are embeddings. That would be a fair way of saying it. I touched on one. One use case for this is semantic search. So you can take a vector database like Redis, and you can fill it up with data and the embeddings that you've created, the vectors. So here we have some meme topics. This is text. Deletion is 100% file compression. TypeScript is just JavaScript for C# devs. Changed my mind. And code doesn't compile, compiles it again. So we've got these stored in a vector database. We have embeddings sitting there next to them. And then when someone looks for something, say, don't need to debug your code if it doesn't compile, then we can create a vector using a model of that meme text, and then search and see, is there anything close to it? Give me the 5 closest or the 10 closest, the k nearest neighbors. And so you can search for things that have meaning. So if we, for example, say, show me memes about fast food restaurants, it knows that McDonald's and Burger King and Wendy's and Arby's are all fast food restaurants, even if the word fast food restaurant isn't in there. And matches them. So this is very powerful. My demo is semantic search with images. Another option is semantic caching. I think this is actually pretty cool. It's kind of exciting, actually. Semantic caching is basically semantic search with a range query. And the idea here is that you can cache things that LLMs spit out. So if a user asks the question, can you explain to me what a dank meme is? That sounds like something Grandma discovering the internet might ask. We can ask the LLM, and that's expensive. Or we can create an embedding of a bunch of questions that people have asked before, maybe as it's happening. And so we turn Grandma's question into an embedding. We search our cache and say, has answers to this question or similar questions been provided before? So what's a dank meme? I don't understand dank memes. Can you explain to me what a dank meme is? These are similar questions. They have the same semantic content, but they're just phrased differently. And so we find an answer to that question that's cached, that came from an LLM from a previous user asking it, and we can just return it. And now we get an answer to a question without having to hit the expensive LLM. Very powerful. If you get a miss, where there's not a result that matches it, then you go ahead and ask the LLM the question, cache that in, return it to the user, and cache it with the embedding of the question. And so now when someone else comes along and asks a similar question, they can get the cache copy instead of having it the LLM again. This is a basic implementation of the cache aside pattern using vector search. So I think this is actually a really powerful option to squeeze more money. If you're asking about blurry photos versus photos out of focus, it's the same question. Give the same answer. This also comes up in everyone's favorite topic, retrieval augmented generation. Everyone's sort of retrieval augmented generation. Yeah. It's a pretty straightforward thing, really. The idea here is that you can provide context to the LLM and then answer questions. So Grandma asks, can you explain to me what a dank meme is? And the LLM, who's not necessarily been trained on dank memes, although this is the internet, we know it really has. If we go and ask the LLM, it's not going to have a good answer. So instead, we have a database full of documentation about meme lore and what memes are and what dankness of memes are. And so we can query that using an embedding, do a semantic search against all of our documentation, pull back things that are relevant to the question, hand that to the LLM saying, given the following context, big pile of documents I queried from a database, answer the following question. Can you explain what dank meme is? And this is literally as if I went into ChatGPT and said, given the following, enter, and then I typed a bunch of stuff, answer this question. This is the process that's happening. And then we give that answer to the user. Now, you can combine this with semantic caching. So if people ask similar questions, you can still go to the LLM and ask, but do it in a RAG fashion. You do not need to use vector search to retrieval augmented generation. You could simply do SQL statements if you have a way of doing relevant queries for what the user's asking. The idea is that you just retrieve something and it provides additional context to the LLM so that about things it has no way of knowing. So that's sort of vector search 101. Any questions so far? Your stunned silence is very reassuring. Sure. Right there?
Ryan, can you explain a little more how you're getting this vector?
Yeah, sure, absolutely. So the question is, can I explain a little bit of where is this vector coming from? So you're taking that text and you're sending it to a model. Its purpose in life is to turn text into embeddings. That's what the model's trained to do. And so that model then pulls out multiple values that have different features, different things that this text is about, and then provides a set of numbers that represents that. And then once you have those numbers, you're just checking the similarity. So there's a model that sits between your text and the vector. Yeah?
Is that a typical size of the vector that would be created, or is that like a medium?
It's an abstraction. The models I'm using, I'm using an image model. So the question is this a realistic size? The answer is no. They're usually hundreds. So the model I'm using for images is 512 dimensions. So there's 512 values in that vector.
So does the length of this vector depend on the length of the text you're...
Yeah. So the question is, does the length of the vector depend on the length of the text? The answer is no. The model spits out a fixed size. So that's just what the model spits out. If you have not a lot of text, you may have a lot of zeros in there, but it's a fixed size. So I'll do one more question, then I'm going to plow forward. Yeah.
So if you have like high dimensional space, will these vectors, the distance between, when you're calculating the distance, does it become like too distant from each other?
Well, yeah, that's actually is the thing that's happening. That's a really good insight. So the question is if you got like a 512 dimensional array or a coordinate in a 512 dimensional space, and you're trying to see how far apart the points are the lines going to be longer? And the answer is totally. They will totally be longer. But ultimately, because everything in that space is in the same dimensionality, those lines are all the lines are going to be in the same playing field. So And because you can't compare vectors that have different numbers of quantities in them. They have to be identical. And usually, all my examples, I use 32-bit floating point numbers, and the model I use for the demo is 512 dimensions. So, cool. Let's plot forward. And I'm going to show the code for how all this works, too. It's actually a lot simpler than you might think. Go ahead and get through here. Because I want to talk a little bit about something you shouldn't do, but I think is interesting to understand. And that is how you could create models on your own that you could use to create embeddings. And then I'm going to tell you not to do it, unless you're a data scientist, which, being a bit of a data scientist myself, I have done. No. Actually, I haven't done this. I have created convolutional neural networks, but I haven't used them for this purpose. So, but understanding how they work is useful. And I'm going to go kind of to first principles because I don't want to leave anyone behind. And so I'm going to go back and just talk about how neural networks themselves work. We've probably all seen this picture here of a neural network before. This is a really common representation. So in this neural network, you've got an input layer, and these are just numbers, floating point numbers. And then all of those numbers in each node flow to all of the nodes in the next layer. And in each of these neurons, each of these nodes, computation happens. These numbers are transformed. So if X is like 12, 12 is fed into all of those things in the next layer, and computation happens there, and then that value is fed into the next layer, and so on. And then you get an output layer. And what this is a function. I give it 4 numbers in, it gives me 3 numbers out. It's a function in the mathematical sense, and in the programming sense as well. Each of these individual neurons in the neural network are also functions. They have an input, actually they have many inputs, but we're going to look at a single one, and they have an output. And so if I put X in, I get Y out, and I could draw a line. I could chart this, I could plot this. Inside of your basic neuron here is a weight, and that weight is multiplied times the input. So if I put in a 12 and the weight is 6, then I get whatever 6 times 12 is, 72. And then a bias is added to that. Now these numbers that are in these neurons are computed when you train the network, and it uses a whole bunch of calculus that frankly I don't understand. And so we're not going to go into that. But the actual way it computes it, once it's trained, is pretty straightforward. It is literally this formula. Input times the weight plus the bias equals the output. And if anyone remembers high school algebra, you might recognize this formula. It's y equals mx plus b, where the weight is the slope. It makes the angle tilt back and forth, the line. And the bias, is the y-intercept. It lets you slide the line back and forth. And so a neuron is a linear function. It creates a linear output. Now, neurons have multiple values, and so instead of creating a line in a 2-dimensional space, it creates a plane or a hyperplane in a hyperdimensional space, but it cuts a space in half. The problem is that not all of our problems are linear. If I take a linear function and feed it into a linear function and feed it into a linear function, what am I going to get out? I'm going to get a linear function, right? And so we add activation functions to the neurons, which will transform that output. There's a few popular ones, and there's one that everyone uses. There's a sigmoid, so you can get it to be a value from approaching 0 to approaching 1. That's one option. You can go hyperbolic tangent, which is basically a tall sigmoid. It approaches 1 and -1 instead of 0. Or you can use what everyone uses, which is a rectified linear unit. And this is just max x, comma, 0. So it's either 0 or it's positive. If it's negative, it becomes 0. But what happens is that when you put these functions on the end of the neurons and put them in a network together, instead of the network drawing straight lines, it starts drawing curvy lines, which can represent realistic things. And so here's a more realistic neuron where you've got inputs and weights, which are all multiplied together and summed. A bias is added, an activation function is called, and you get an output. So each of these neurons are functions. And this is the output of that. It's the sum of the inputs times the weights plus the biases. And a sigma is as mathy as I'm going to get. So that's a basic neural network in 3 minutes. So hopefully it was a review for many of you. A convolutional neural network is a specialized kind of neural network where you restrict the connections in it. So not every node is connected to every node. And it creates a hierarchy of image classification. So it takes all the pixels and can find patterns in the pixels, and then it takes those patterns and finds patterns in those patterns, and then patterns in those patterns, and so on, so that you start out by finding lines, and then you find shapes, and then you find features. And so, you have a filter that represents a line going up and down, and then that outputs a map of where lines going up and down are at throughout the data set. And then you can say, well, everywhere that I've got a line up and down and a line left and right, what's that? And then it starts identifying more and more complex shapes. Here's a representation of that. We've got on the left here my attempt at a stick figure troll face. I actually think it kind of looks like the troll face. And these filters are patterns that you're matching in it. And so it pans and scans across the image. And then on the left here, my pointer over there, wherever it finds this shape, for example, it marks it in that output. So it's creating a map of everywhere that 3 crossed lines. I like that the eyes actually look like eyes in the next image. A little more of an animated way to show this is it goes across the image. And so we literally will look at this and say, does it match this pattern, yes or no? No, no. And we just scan across the image. My pointer's too slow for this. And then when we get a match, right? The match right there, we put a dot. There's another match, and then not another one. And so it's doing that for lots of different filters. Now, of course, we don't just have Booleans in our neural network. That's not what we're operating on. We're actually operating on numbers. And so these bits in the image represent 0 to 1 from how dark or how light the pixel is. The filter has a bunch of numbers in there. You'll notice I added a little number at the bottom too. Spoiler alert, that's the bias. And then the output is the result of doing math on the filter plus the input. And that math is what we just talked about in neural networks, because all the values in the image are the x's. And the filter are the weights. And the output is the y that's run through an activation function. So this is doing that same process for each neuron, but the weights in the filter the filter is actually just a series of weights. And then this allows you to identify these things, and then you can concentrate them down. So sometimes there'll be little pixels that will be set in an image that might confuse the image. Like if you had a line and there's a little bump in it, it's still mostly a line going down. Pooling is a way of taking and compressing them down, basically scaling down the pattern. So like this here, we're going 2 by 2, and if there's something in here, then we mark it, and if there isn't, we don't. And so here we've taken that output of the pair of eyes and compressed it down. And here it is with numbers. In this case, the compression down is take the maximum number in that 2 by 2 area. We create a map of that. Once we have all these numbers, we can then flatten it out and just take that pooled output and just map it, just flatten it out and make it one long list of numbers. And that's our feature set. These are numbers from 0 to 1 that whatever the model does, that represent the features that model's identified. If you're training these things, you need one more layer with a bunch of classes on it so that it has something to train against, and then you rip that final layer off, and then you've got your convolutional neural network that can create image embeddings. This is not the only way to create image embeddings, it's the way that I know. That's the one I'm sharing. So, how are we doing on time? I got about 15 minutes, I think, right? 10 minutes? I think 10 minutes. We'll say 10, that way I'm not late. So, now you're a developer, and you're like, you could build what I just described using Keras. I've built it to classify Viking runes in a talk that I did several years ago called Deep Learning Like a Viking. And it was a lot of fun, and you're probably like, I kind of want to do this. Well, you should totally go ahead and do it for fun, but don't do it for prod, unless you're working with someone. It's tempting, and you want to play with the toy, right? But one does not simply create their own embedding models. A lot of data scientists have gone to a lot of trouble to figure out how to solve this problem. And as a developer, you might be, well, we get that thing as developers, or maybe it's only me. It's like, yeah, I can do anything. And then I start coding and I'm like, oh God, I'm an idiot, right? If you pair with a data scientist, and you could do this, but lots of times you don't need to. The models are out there, they're pre-trained, you can pull them down off a Hugging Face and just use them. So that's what I recommend instead. Don't build your own CNNs. Understanding how a CNN works, how the neural network works, can influence help you understand. Like I've got this philosophy that I should understand the technology I'm working with one layer below. Because when it makes weird errors don't make sense at the level of the technology, you need to parse them out from the layer below. So knowing this is useful, but you probably shouldn't do it. So let's go ahead and do the demo now. Y'all got any more of those vector database demos? The demo is going to use Redis, obviously. Not saying I'm going to use Redis, but I'm going to use Redis. And so what I've built is basically a fairly straightforward semantic search using Redis as a vector database and using Hugging Face transformers. You can actually run Hugging Face transformers in a browser. I don't in this demo, but I need to convert it over to a browser-based implementation. Or in Node, I'm just using it all in Node, but it works in both places. So what I've built here is I've got an instance of Redis, and I've got a little meme loader tool, just a little command line tool. It runs inside of Docker. What the meme loader does is it creates an index inside of Redis that says, index all these fields. I'm going to give you a bunch of hashes in Redis. And those hashes are going to contain text and some numbers and stuff like that. And also an embedding. And so create an index and look for those. The embedding is in a particular field, and the title is another field, et cetera. Then it pulls a bunch of memes from the hard drive. This is out in GitHub. Creates embeddings for those images, pulls the title off the file name, and writes it out to Redis in a key, using like meme, twin, colon, and then a kebab case version of the title. And now Redis has an indexed database of 72 meme images that are in that folder and has embedded them. So now you can do semantic search. So how do we do the semantic search? Well, we got a little client, which you saw earlier. The client will take a picture of you. He will send that photo to the meme server, which will embed that photo. It will use that index that we created to search Redis to find matching memes. It will then fetch the image out of Redis and the title and hand it back to you and render it on the screen. So we've already seen the demo work. I'm going to show you the code. And then we'll see, and then anyone who wants to come up and try it can try it. If we have time, I think we have time for that. So let's take a look at some code here. I guess I thought I only had 50 minutes, so. Well then we'll do everyone. I know we got a break time scheduled right after that. I didn't want to cut into that, so. Okay, let's go. I probably should have signal closed, shouldn't I? Someone's going to freeze for a minute. It's like, oh my God, what was he talking about? Okay, so here's the code. I'm going to go ahead and this is all Dockerized, so you can literally fork this repo, do docker compose up -- build and run it. So I've got in here, I'm going to look at the meme loader first. So in here, here's all my memes. So here, we got Afraid to Ask Andy, Disaster Girl, The Drunk Baby, Grumpy Cat. So hot right now. I've never had anyone match as stonks, but I hope it happens someday. So I got a whole bunch of them in here, right? And this is just the folder that it reads them from. Here's the source. I've got, in this case, we'll look at main here first. Main there's nothing particularly brilliant about this code. I literally get a directory of the folder, filter out anything that's not a PNG or a JPEG, log the fact that I found one, extract the title from the file name, get the image path to read the file. And then I got this little function called embed, which is where the magic happens. that takes an image file, a path, a URL to an image. It can be a path on the hard drive, it can be a URL on the internet, and it will download it and render it, create an embedding out of it. And then here I create a kebab case title of the title for a key in Redis. And then here's the one bit of Redis where I say set this key, and I give it a title, the bytes that make up the image itself, and the bytes that make up the embedding. Those get written out to Redis, and that's all this does. So is that text big enough? I should have asked that before I went through it, right? So the embedder, which is really the interesting part, is really short. So I bring in Hugging Face transformers. This is a JavaScript library. There's also a Python version of it that is designed for building these pipelines to do things like image feature extraction, or even calling LLMs. There's lots of models that they work with. I'm just doing feature extraction, image feature extraction. So I create a pipeline that is called image feature extraction. And what that's going to do is, that says you're going to be given an image and you're going to get a URL, so you need to be able to download it and then resize it and make sure it's square and then run it through the model. And the model I used here was Zenova ClipVit base patch 32. These model names are always so meaningful. And then just some arguments to say we're doing floating point 32-bit numbers here. And then it's just a matter of calling this extractor, this pipeline that it created, giving it the image path, and it returns a tensor. And that's actually all you really need to do. However, I just want the raw data out of the tensor. I just want the embedding bytes itself, or the embedding values itself, and that's a float 32 array. And then I have to convert that to a buffer from the buffer to make Node Redis, because I'm working with Node. Node Redis wants a Node buffer as opposed to a JavaScript byte array. So, but that's all the code for creating the embedding. If you do this in the browser, line 10 is removed, but the code's the same. In the Redis client here, I've got a few types up here, but the main thing here is I create my client to connect to Redis, and then I've got a little create index function. I create 3 indexes because I want to be able to compare cosine similarity versus inner product versus Euclidean distance. So I create 3 indices. And then I assign the index I want to use by default. But here's the salient part of this code is the create index. And so I drop the index if it exists already so that I can recreate it. It's kind of lazy coding there on my part, honestly. We call create, give it an index name, and you say, okay, well, the title in this index is a text, so if you wanted to search for all the memes that have the word cat in it, then you can just do a keyword search. And the embedding is of type vector, and here we provide the algorithm, that's flat versus HNSW. We say that this vector has 32-bit floats in it. We say that this vector has 512 dimensions, and this is straight from the model. The model creates 512 dimensions, so I need to tell the index you're going to get data that has 512 dimensions. In other words, you're getting an array with 512 elements that are floating, that are float 32s. And then I give it the distance metric, which is a parameter here because I want to create multiple indices. So that'd be L2 or cosine or inner product. I'm doing this on hashes, not JSON documents. And the prefix is just look at any key that starts with meme : twin : So that's all it's doing. And that's pretty much it. That is creating a bunch of embeddings. This runs once when you Docker compose up, it's run. The meme client is just a bunch of image capturing and HTTP fetch calls and that kind of stuff. And we're not going to look at that because it's just boring front-end code. You can go look at it later on your own. There's nothing interesting there. I wrote it in vanilla.js. So we'll look at the server instead. On the server, we have exactly the same embedder. I actually just copied and pasted the code. I don't always reuse code, but when I do, I copy and paste. I mean, I could shove that in some common library, but there really isn't enough there to justify it, honestly. Main is just, this is an Express app, and this just calls into functions that do things. The matcher is where the interesting bit is, and so the matcher has a find match function. It takes that image data as a buffer. That's the image that was posted from the camera in the web browser. And then I build up a query. Vector searches in Redis have two pieces. There's the search query, which is your conventional search. Give me anything that has the word cat in it. Or give me things above a certain number, that kind of stuff. Structured data searches. The vector search portion is I want my k nearest neighbors. I want one of them. I want you to look at the field embedding, which is where I put the embedding in the hash. And then I've got a parameter for you called blob that will be passed in when you invoke the function. We paste these together into this little structure here. So it's basically, it kind of looks like calling a Lambda function where you got parentheses, fat rocket, and then square brackets. And the parentheses have the star, and between the square brackets, you have the k nearest neighbors bit. And then here's the fun call to embedding. There's actually I had to write the image to the disk and then delete it afterwards to make this work, so that's all this is doing here. So we call embed, it works exactly the same. Now that we have our embedding of the photo that we took from the webcam, we can then search. Here's our embedding we want to search with. There's the blob that we mentioned earlier. We sort by the embedding score, say I only want one thing, and return the title of the image and the embedding score. And so that does a vector search. Well, it almost does a vector search. We have to call search there. We pass in the index name, the query that we just built, and any options. And that's pretty much it. I got a little fetch image down here. All it does is an HKit. It's not fancy. Yeah. So that's the code. You want to see it do its thing again? Hell yeah, right? Okay, so start over. Please, oh God. Okay, so you notice down here I've got cosine, inner product, and Euclidean. You click these, it will change the index. It'll change the alias. So we're going to go right now. Let's go with cosine similarity. I am going to try and get my camera to work one more time here. And that may turn into me unplugging this thing again. Okay, here we go. This is like totally probably messing up with the live stream. I apologize. There we go. We'll see if that works. There we go. Okay, so I'm doing cosine similarity. Let's see who I show up as. Okay, if I go to Euclidean, start over. And if I go to inner product and start over, this is usually Grumpy Cat. Yeah. I think it's just picking up on all the hair when I use the inner product. So yeah, that's pretty much my demo. I got 2 slides, and then we can have people more slides, and we can have people come up and actually do this. That sound good? Okay. Let's go back to here. I'm just going to go ahead and I have a feeling it's full screening it that might be messing with the camera. So I'm just going to do this from inside of PowerPoint. So if you want to play with the code, it's all out there. You can scan this QR code, download it, Docker Compose up yourself, run it on your laptop. Should work just fine. I work for Redis, obviously. If you want to learn more about Redis, we got university courses, some of which feature my voice. And you can learn more at redis.io. We have a Discord server if you have questions at discord.gg/Redis. I'm pretty much the person that maintains that, so if you ask questions and I have an answer, it will be coming from me. If you say, hey guy, I saw your talk at Devnexus and I have a question about it, and you tag me, I'll answer it. And just shout out here a little article here. This is on the performance metrics. Obviously, there's lots of vector databases out there. Every database is adding a vector feature. And this basically just says that Redis is the best. It's a benchmark. Take it with a grain of salt. It's got truth, but also, right? All I can say with confidence is that our numbers are way better than Mongo's. Sorry, Mongo. Love you, but yeah. Not trying to talk smack. I have a lot of good friends there. So those are my slides. This is how to get a hold of me. And let's go to the fun part of having a few people come up and find out who their meme twin is. Who wants to be first? Come on up, one of you. And we'll start over here. Okay, the camera's still working. So you can go ahead and stand up here. And I have found that it tends to just look at gray hair, white guy, and make you either Paul from American Shoppers or most interesting man in the world. So, and yeah, go ahead and click take photo. Okay, and then if you like it, use it. Yeah. Try a cosine similarity instead. Yeah, there you go. Yes.
All right, I see it.
Yeah. You are clearly the most interesting man in the world. I thought I was, but then I realized I was just narcissistic.
Yep. 2 out of 3.
Yeah, there you go. Anyone else want to do it real quick? I'll just get out of the way here. I didn't put anything inappropriate in the meme database, so you're good.
So is there anything actually stored?
Is there anything actually stored in Redis?
Yeah.
So in Redis, I have stored the title of the image, the actual bytes making up the photograph,
So there's any result of recognition.
and the vector. Yeah. Yeah. Okay.
Let's see with the head.
Yeah.
Are they the same size?
No. Yeah. So there's a question about with text to image. There are multimodal models where you give it text that describes something and an image that describes something, and they will create similar vectors. So you can do so I can do text.
Compare vectors of text and
Vectors generated from text and vectors generated from images will be similar so that you can do search. So you can do like semantic search with text and find images. Yeah, go ahead.
Understand more about the decimal numbers. In the example you gave in the beginning, it was very clear alcoholic and